Okay, so this slideshow contains the information that you will need to answer the take-home question that's on the final test. I think that's worth about 6 points. You can do this in your own time, or you can do it on the day, or you can do it on the day of the test. It's your choice. What we're going to be talking about is how we can relate battery capacity, that is the capacity of a battery to do work, to the quantities of reactants. Now, obviously, the more reactants that we have in a battery, the more electrons that can be transferred, the more work that that battery can do. The next topic that we'll look at is the concept of electrolytic cells and rechargeable batteries. So all of the cells that we've been looking at so far are voltaic cells. They are cells that there is a spontaneous flow of electrons, and we don't have to do anything to make those electrons flow. The other kind of cells are cells that are called electrolytic cells, in which the reaction is non-spontaneous and we actually have to do electrical work to make that reaction occur. And the classic example of that is the rechargeable battery. So 19.7, relating battery capacity to the quantities of reactants. So clearly, as we increase the quantity of reactants, we will increase our battery capacity. But how are those things related quantitatively? So you've probably, thought about the capacity of a battery. You know that when a battery runs flat, it no longer has the capacity to do any work. So when we look at a cell, how do we know how much work a cell can do? And you see this recorded on cells. Here it is written here. It says the capacity of this particular AA cell is 2,500 milliamp hours. So it's not really clear what this means. In particular, what's this term amp mean? And how do they come up with these units? We probably know what millis is, and we probably know what hours is. Also noted on the cell is the potential of the cell, the E cell, and that, as you've learnt to recognize, is determined by the anode and cathode half reactions. The capacity of the cell, what do you think determines the capacity of the cell? Well, it's the size of the cell, isn't it? It's the amount of reactants that are present. So the amount of work that can be done by a cell is the charge transferred multiplied by the potential of the cell. So that's the amount of work that can be done by a cell. This is determined by the cell chemistry. It's an intensive property. It depends upon the identity of the anode and cathode reactions. The quantity of charge transferred is an extensive property. It depends upon the amounts of reactants that are going to be consumed. The more reactants that are consumed, the more charge that is transferred. So let's have a look at this cell. It's our copper-silver cell, and electrons are going to flow from the copper electrode into the silver electrode, reducing silver plus. And then it says how much work is done by the cell if it is operated until 2 grams of copper solid is consumed. So we need a balanced overall reaction, and then we can think, well, for every mole of copper that is consumed, I will generate 2 moles of electrons. So from there, I should be able to figure out my work, right? Because my work is just the cell potential multiplied by the charge transferred. So if I can figure out how many moles of electrons or how much charge is transferred, and then using my standard reduction potentials, I can get cell potential, I should be able to solve this problem. So here it is. So how many moles of copper are going to be consumed? 2 grams times 1 on the molar mass, 0.03147 moles of copper. And for every mole of copper, I generate 2 moles of electrons. So the amount of charge that's going to be transferred will be my number of moles of electrons, which is 2 times my number of moles of copper, or 0.06294 moles of electrons, multiplied by Faraday's constant, 96,500 coulombs per mole. So what I'm really saying is that consumption of 2 grams of copper is equivalent to production of 6,074 coulombs of charge. Okay, is the number of moles of copper. For every mole of copper consumed, I get 2 moles of electrons. Multiply my moles of electrons by Faraday's constant, and I get the amount of charge transferred in coulombs. The work then is simply the negative of the charge transferred multiplied by the cell potential, which we determined previously from the cathode reduction potential minus the anode reduction potential. potential to be 0.4577 volts. So multiply these two numbers together, and the amount of work that is done by the cell, so that's why this is a negative number, is minus 2,780 coulomb volts. And a 1 coulomb volt is the same as a joule, right? We mentioned that before. You can divide this by 1,000 and you can say it's minus 2.78 kilojoules, which is done by the cell. That's why it's a minus sign here, because the cell is doing work on the surroundings. Okay, so cell capacities, you've probably noticed, are not reported in joules. They're kind of often reported in funny little units like milliamperes, hours. So what do these units mean? And in particular, what the heck is an ampere? And so an ampere is the SI unit for electrical current, and 1 ampere equals 1 coulomb per second, or 1 ampere second equals 1 coulomb. So a rating of 2,500 milliampere hours is really a measure of coulombs, because we can measure coulombs in amperes time. You see up here, so this is kind of amperes and this is time in this case, but it's done in a really weird kind of way, but it's really saying how much charge this battery could transfer. And if we converted this milliampere hours into amperes per second, that would be equivalent to coulombs. So here we go. It says, here's an example. It says, which of the following voltaic cells will produce the greatest quantity of electrical charge per gram of anode material? And so we've got two reactions here, cadmium plus this nickel oxide hydroxide stuff, producing just nickel 2 hydroxide and cadmium hydroxide. And then we've got aluminum reacting with oxygen in the basic solution to produce this anion here, aluminum tetrahydroxide anion. So in each case we need to identify what is the anode and cathode process, and then we can get a cell potential, and then we've got to calculate how much charge would be transferred when 1 gram of the anode is consumed. So we'd be turning that gram of anode material into a number of moles, and then turning that into a number of moles of electrons, and turning that into a charge, and multiplying it by our cell potential. So let's look at the first one. Cadmium solid goes to cadmium 2 hydroxide, so clearly the cadmium is being oxidized. And in the second one, we've got aluminum solid with an oxidation number of 0 going to this aluminum tetrahydroxide anion over here. So the aluminum is going from 0 to +3. So in the first case, cadmium is the anode, and in the second case, aluminum is the anode. So if 1 gram of cadmium is oxidized, how many moles of cadmium would that be? So that would be 1 mole of cadmium divided by its molar mass. So it's this number of moles of cadmium. Now for every mole of cadmium oxidized, I'm going to get 2 electrons transferred. So I've got to times that by 2 to get my number of moles of electrons. So this gets me my number of moles of electrons, and now I've got to times this by Faraday's constant to get my coulombs. So this converts from moles of electrons to coulombs, and I've done the dimensional analysis here. So for every gram of cadmium oxidized, I'm going to get 1.72 by 10 to the 3 coulombs of charge transferred. And then I do the similar activity for the aluminum. So aluminum is being oxidized by 3 electrons. So for every mole of aluminum oxidized, 3 electrons would get transferred. So here we go, 3 moles of aluminum per 1 mole of 3 moles of electrons per 1 mole of aluminum, and I get 1 mole of aluminum per 26.98 grams. So this is going to get me per gram of aluminum. And then here we are, we've got 96,500 coulombs per mole, just Faraday's constant. That's going to get me the amount of charge transferred per gram of aluminum. Okay, so 3 moles of electrons per mole of aluminum. In 1 mole of aluminum, there are 26.98 grams. So this gets me moles of electrons per gram of aluminum. and then multiply it by Faraday's constant is going to get me coulombs per gram of aluminum. So moles of electrons cancelled out, moles of aluminum cancels out, leaves me with coulombs per gram of aluminum. So we've seen energy expressed in different forms depending on the situation. The SI unit for energy is the joule, which is actually equal to 1 kilogram per meter squared per second squared. And when we often use this sort of kilograms meter squared per second squared when we're doing the Einstein mass energy relationship, E equals mc squared, or when we're using the de Broglie wavelength. And you'll recall that we always have to use kilograms in these formulas in order to get sensible results. The other way that we've seen energy expressed is when we're working with electrochemical cells, and we can say that 1 joule equals 1 coulomb volt. And we noticed before that we could express a coulomb in terms of ampere seconds. So we can rewrite this. We can say that 1 joule equals 1 coulomb volt, or that equals 1 ampere second per volt. And then to complicate matters even further, electrical energy is often reported in terms of power, and power is the amount of energy transferred per unit time. So power can be defined as energy transferred per unit time, and the SI unit for power is the watt, and 1 watt is 1 joule per second. And this was named after James Watt, who's the guy who invented the first commercially successful steam engine. He was from the University of Glasgow, which is rivals to the University of Edinburgh where I used to work, and it's in honour of James Watt that in Star Trek, you always have Scotty as the engineer, because it's honours the Scottish engineering tradition. So we could write an expression for energy in terms of watt. 1 joule equals 1 watt times seconds. So 1 joule equals 1 watt per second. But 1 joule is not a lot of energy, and 1 second is not a lot of time. So often energy is expressed in terms of what we call kilowatt hours. And when you get your power bill, that's what it's expressed in, right? It says the usage is so many kilowatts per hour. This is a measure of energy. It's the measure of the number of joules. So this is what this is measuring. 1 joule equals 1 watt per second, and if you wanted, you could do the conversion, figure out how many joules are in a kilowatt hour. So here we are. It says electrochemistry and the quest for clean energy. So battery capacity is related to the quantity of reactants. The amount of work a chemical cell can do is directly proportional to the amount of electrical charge you can transfer from one half cell to the other. So this is the key relationship here. So if one can figure out the number of moles of electrons transferred, and if one knows the cell potential, then one can figure out the work that a particular cell can do. There are a whole bunch of ways to describe energy, whether it be in terms of joules, whether it be in kilograms meters squared per second squared, whether it be coulombs volts, or whether it be ampere seconds volts, and sometimes watts per second. But the most appropriate units depend on the context. These guys are good for when we're dealing with problems concerned with mass energy equivalence. This may be more useful when we're thinking about electrochemical cells, and this guy might be more convenient when we're thinking about how much power we're consuming in our home. Alright, so now we're going to move on to the topic of electrolytic cells and rechargeable batteries. And as I said before, electrolytic cells are cells where we actually have to do some electrical work in order to make current flow. So, just recapping, electrochemical cells can be divided into two classes. The first, which we spent most of the time talking about, are what we call voltaic cells. They have a spontaneous reaction, delta G is negative, and the cell potential is always positive. Those types of cells can do electrical work on the surroundings. An example of this kind of cell would be a battery. The alternative type of cell is an electrolytic cell. In an electrolytic cell, the overall cell reaction is non-spontaneous, that is, delta G is positive and the cell potential is negative. Those cells require an input of electrical energy in order to make the reaction occur. And the classic example of this is the reaction of electroplating. We put an electric current into the cell and we force a metal to be reduced and coats out onto the electrode. So in a battery, a spontaneous reaction occurs, that is delta G is negative and the cell potential is positive. So when a battery is discharging, electrons will spontaneously flow from the anode into the cathode, and we can intersect those electrodes and get them to do useful work on the surroundings. In this case, it's lighting up a light bulb. So a classic example of that is your lead acid battery that's in your car. And in the lead acid battery, we've got a couple of things going on. The reduction reaction is lead sulfate gets reduced to solid lead, and the oxidation reaction, the anode reaction, is lead sulfate, lead 2+, gets oxidized to lead 4+ in the form of lead 4 oxide. This all takes place in acid solution, and so that's why it's called a lead acid batteries. Now, these guys are all, the products in each case are solids, so the reactions are taking place on the surface of the electrodes. When a battery is recharged, you have to put in an external source of electricity to drive the non-spontaneous reverse reaction. So in this case, our anode, what was our cathode becomes our anode, and what was our anode becomes our cathode. And instead of there being a spontaneous flow of electrons from left to right, we are now putting in a power supply and we are forcing electrodes into the cathode. So recharging a battery is an example of electrolysis, which is a process in which electrical energy is used to drive a non-spontaneous process. So here we are, the spontaneous process. Electrons flow spontaneously from the anode into the cathode, and we can intersect them and get them to do useful work. When we're recharging a battery, we use a power supply to drive electrodes from the anode into the cathode, and we have to do the work to make that non-spontaneous process occur. Notice that while the anode becomes the cathode, and when the anode becomes the cathode when we are recharging a battery, the signs of the battery don't change. The polarity of the batteries is the same. Okay, so your cathode is now negatively charged and your anode is now positively charged when we're recharging our battery. So a well-known example of this, which we talked about before, is your lead acid battery. And so here is the spontaneous reaction. In this case, it's solid lead getting oxidized to lead sulfate is your anode reaction, and your cathode reaction is lead 4 oxide being reduced to lead sulfate. When we are recharging, when the alternator in your car is recharging the batteries, the anode becomes the cathode and the reverse reaction occurs. The cathode becomes the anode and the reverse reaction occurs. So we learned about current before. 1 ampere is equivalent to 1 ampere per second. So a useful question is, how long is it going to take for a particular battery to recharge? So here's the example, and this is what's really on your take-home problem. If a battery charger for a lead-acid battery supplies a current of 2 amperes or 2 coulombs per second, how long does it take to convert 0.65 grams of lead sulfate to lead? So this is our cathode reaction, and we can see that for every mole of lead that's produced, 2 electrons must be transferred. And the electrons are being transferred, or charge is being transferred at a rate of 2 coulombs per second. So if we figure out the number of moles of lead, then we can multiply that by 2. That will give us the number of moles of electrons. Take the number of moles of electrons and multiply that by Faraday's constant. That will give us the amount of charge being transferred. And we can then use our amperes, our current, to determine how long it will take to produce that amount of charge. So the number of moles of lead is the mass on the molar mass, or the number of moles of lead sulfate that we are going to convert, mass on the molar mass, here it is. So 2.143 by 10 to the minus 3 moles of lead sulfate. Now I get 2 moles of electrons per mole of lead sulfate, so I've got to multiply this number by 2. I'm going to have 4.287 by 10 to the minus 3 moles of electrons transferred. I don't want moles of electrons, I want the number of coulombs. So I've got to multiply this guy by Faraday's constant, which is what I'm doing down here. So I take my moles of electrons and multiply it by Faraday's constant, and that gives me the amount of charge that's being transferred in coulombs. Now, the current is 2 amperes, which is equivalent of 2 coulombs per second. Or in 1 second, 2 coulombs will be transferred. So here I've got 1 second, 2 coulombs transferred, multiplied by the total number of coulombs I want to transfer, and it tells me it's going to take 206.8 seconds transferring current at a rate of 2 coulombs per second to convert 0.65 grams of lead sulfate into solid lead. Alright, so another common example is electroplating. So here we've got an anode, and at our anode, silver is being oxidized to silver plus. And then we've got a cathode, which is our spoon that we want to coat in silver, and at our cathode, silver ions are being reduced to silver. So if I can make this reaction occur by using a power supply, I'm going to take electrons from my anode, which has to be hooked up to the positive terminal of my power supply, and then I'm going to push electrons into my cathode, which must be connected to my negative side of my power supply. So the sign convention of the electrodes is reversed when we're doing a non-spontaneous reaction. So a typical question to ask is, how long will it take to plate 1 kilogram of aluminum solid from aqueous aluminum 3+ with a current of 100 amps? So my oxidation reaction is aluminum 3+ being reduced by 3 electrons to aluminum solid. So I want a kilogram of aluminum, so if I can get the number of moles in 1 kilogram of aluminum, if I multiply that by 3, it'll give me the number of electrons I need to transfer. If I multiply my number of electrons by Faraday's constant, that'll give, or my number of moles of electrons by Faraday's constant, that'll give me the charge that needs to be transferred. And then I know I'm transferring charge at a rate of 100 coulombs per second. So let's do the calculation. Number of moles of electron that I wish to produce is 1 kilogram, or 1,000 grams, and there are 26.98 grams per mole is the molecular weight of aluminum. So I want to plate 37.06 moles of aluminum onto my spoon. So it's a big spoon if it's 1 kilo, isn't it? But that's how much aluminum I want to transfer. So I've got to times that by 3 to get my number of moles of electrons. Okay, so times 3. So I want to pass 111.19 moles of electrons. Multiply my moles of electrons by Faraday's constant, and that's going to give me my number of coulombs, which is 1.073 by 10 to the 7 coulombs. Now I'm passing current at a rate of 100 coulombs per second, or alternatively, in 1 second I'm passing 100 coulombs. So I take this number and multiply it by my number of coulombs, and it tells me it's going to take 1.073 by 10 to the 5 seconds to plate out a kilo of aluminum.